Next 30 minutes, I'm going to try to do my best to make you an expert. Hello and welcome. In these 30 minutes, I will do my best so that you emerge from this short class as an expert in position, velocity, and acceleration versus time graphs. All right, so let's get started. Let's first consider the easiest possible graph. A distance time graph where the distance is not changing. So if this is distance and this is time, let's just imagine that we start at 0 and we stay there for the whole time. So if we're not moving, our velocity time graph would look the same. So if we can just draw on the same axis, velocity versus time, and it would look like that. And if we had acceleration versus time, yeah, there's no acceleration either. So this is the easiest possible graph for distance versus time that we could have, and we can see that velocity and acceleration versus time would look the same. Now, let's do something a little different. Let's say that the distance time graph was still constant, but it didn't start at 0. What's the velocity here? The velocity is still 0. We are not changing our position. We're not changing. And by the way, instead of distance, we can also call this position, as it is often called in physics class. So yeah, I'm going to get rid of distance and we're going to call this position versus time. Okay, so if our position was constant, but it's not 0, well, it turns out for velocity versus time, we're still going to get no change. Our velocity is 0, and our acceleration would also be 0. Okay, so moral of the story here, if you have a flat line in the distance graph, you end up with flat lines at 0 for the velocity and acceleration graph. So that this covers the first case, the easy case. Now, let's do something a little more complicated. Let's say I have a velocity time graph, and it looks like this: velocity versus time. Now, what would the position time graph look like? If I draw on the same axes here, the velocity is constant. What does that mean? That means the position is changing regularly. It's changing at a constant rate. So we end up with a straight diagonal line here. Okay? And what happens for the acceleration? Well, the velocity is not changing. So the acceleration versus time graph is going to be 0 throughout all time. It's going to be a horizontal line at 0. Okay, so this is the second hardest case. Now, let me clear my drawing here, and let me say that this time my acceleration is constant. Now, what would my position time and velocity time graphs look like? Well, if acceleration is constant, that means my velocity is changing at a constant rate. So my velocity is going to be a horizontal, or rather a diagonal line here. And what would my position time graph look like? If the velocity is changing and it's increasing, that means my position is going to increase more and more dramatically over time. So I'm going to get, sorry, let me draw that again. It's going to be a parabolic line, a quadratic function. So you can see the slope is getting more and more. It's getting higher and higher as my graph progresses. Okay? So you can see a horizontal line for the position graph resulted in the easiest set of graphs. Horizontal line for the velocity graph was slightly more complicated, and a horizontal line for the acceleration, that gave us a quadratic function for position. So this one was more complicated. If we understand these, this gives us the basic foundation for all other graphs. So let's recap what we've covered here. Let's draw 3 sets of graphs. Okay, so this is going to be position versus time. This is going to be velocity versus time. And this is going to be acceleration versus time. And let's have 3 of these as I promised. It's going to fit. Okay, that one's not going to fit.